In this video, we move on to section 3.4, which is partial fractions. And the name hints to the kind of integrals that this technique will solve. So the method of partial fractions is used for rational functions, right? And rational functions we know means a fraction, right? Functions that are fractions, right? So basically we'll be given an integral of the form some p of x over some q of x, right? Where p of x is a function, g of x is some other function, right? Where the degree of p of x, the numerator, is smaller than the degree of the denominator. And this is so that we can simplify our integrand. So the method of partial fractions, let's do an example to motivate it. So basically what we're going to do is we're going to break up the integral into two factors. So pretty much what we're going to do is we're going to start with a function that looks like what we said we were going to be given as our integrand, right? One function divided by another. And then we'll keep the numerator the same, but we'll factor the denominator into two factors. This also works with three factors. And then we'll split this up, right? And we'll find an A and a B, capital A and a capital B, so that we can split that fraction up, the numerator up like that. And like I said, we can also do this with three factors. Right, so let's say we start with, again, some function that's of the form p of x over q of x, and then we'll factor the denominator, right? And this time we're going to factor it into three factors, and then we'll end up with three separate fractions that will be simple to integrate, right? Because the capital A, the capital B, and the capital C are all constants. So again, like all of our other integration techniques, we're basically trying to simplify the integrand, right? The function that they give us, in order to make the actual integration easier for us to do. So let's do an example. So it's going to be the integral of 7x plus 13 all over x squared plus 5x minus 14. Right, so again, our job is to take what we're given and factor the denominator. So that's what we're going to do. So we need to take the denominator out. And remember, to factor, right, we have to see what multiplies to the last term, right, or the term that has no x next to it, to the term, and adds up to the coefficient of the term with just x in it. So what multiplies to 14, right? That's 1 and 14, 2 and 7. And is there any more? No, right? So you have to see what combination, right? And this is a negative 14. So one or the other of these numbers is going to be negative. So which one can we add up to get 5, right? Well, we can use 7 and a negative 2, right? 7 plus negative 2 is 5. So this is equals to x plus 7, right? Because we want the 7 positive, and a minus 2. So now we take our integral, 7x plus 13 all over x squared plus 5x minus 14, right? And now we know that we can rewrite the denominator as x plus 7 all over x minus 2. Okay. But, we don't want the final format that we want. Right now we're here, right? We took our denominator and factored it, but we want to be here. So how are we going to figure out what capital A and capital B need to be, well, we have to set that up, right? So we just know that we want these two things to be equal to one another. So I'm going to take my, where I'm at currently, the 7x plus 13 with the factor denominator. And I know that my goal is to separate that into some constant capital A over x plus 7 plus some constant capital B over x minus 2. Right, so we need to find capital A and capital B. Right, but this is an equation. And when we do find our capital A and our capital B, we want this equation to be true. So we can actually use this equation to solve for capital A and capital B. So the first thing we're going to do, right, we're trying to solve for capital A and capital B. So let's try to get rid of the denominators, right? So what we're going to do is multiply both sides by the factor denominator. So we're going to multiply both sides by x plus 7 times x minus 2. Right, so it's going to be x plus 7 times x minus 2 times 7x plus 13 all over x plus 7 times x minus 2 is equals to A over x plus 7 plus B over x minus 2 times x plus 7, x plus 2. Right, and so on the left-hand side, right, if we multiply something by x plus 7 and then divide by that, that's going to cancel out. Same thing with the x minus 2. So those two things cancel each other out. And then on the right-hand side, we're going to have to distribute this to both of those terms. Right, so on the left-hand side, all we're left with is 7x plus 13. And then on the right-hand side, we have A over x plus 7, and that's going to be times x plus 7, x plus 2, plus B over x minus 2 times, at some point I changed this to a plus, small typo there. Okay, and x plus 7, x minus 2. So if you look at this closely, if we divide A by x plus 7, but then we multiply by x plus 7, right, we multiply and divide by the same thing, that's going to cancel out. And then the second term, that happens with the x minus 2. So then we're left with 7x plus 13 is equals to capital A times x minus 2 plus capital B times x plus 7. So now, right, remember our goal is to find capital A and capital B. So one useful trick is basically to just plug in the factor from each of these one by one to solve. So that way we can cancel it, right? Like right now we have two unknowns, and we're going to try to make it just be one unknown that we can solve for, and then we can solve for the other one. So, right, we need to find capital A and capital B, right? So useful, I don't want to call it trick, but for lack of the other term, better term right now, it's going to be a useful trick, is to actually plug in the factors, right? X equals 2, right? Or x equals negative 7 to only have one unknown. Okie dokie. So let's plug in x is 2. So when we plug in x is 2, 7x, right? We're going to take this equation here. Let me just copy it instead of rewriting the whole thing. And we're going to plug in x equals 2 for all of our x's. So that's going to become 7 times 2 plus 13 is a times 2 minus 2 plus b times 2 plus 7. Right, so this is going to be 14 plus 13. A times 0 is just 0. And then, right, so this whole thing is 0. And this is going to be b times 2 plus 7, which is 9. Right, so we have 27 is 9b. And if we divide both sides by 9, we're going to end up with b is equals to 3. So we solved for one unknown. Now what we can do is go ahead and plug that into our formula. So our formula becomes now, right, where we're at is 7x plus 13 is, we don't know what a is, right? But now we know that b is 3. So this is where we're at. So now what we can do is plug in x equals -7 to solve for a. Right, so x is -7. I'm going to take this equation and plug in -7. So 7 times -7 plus 13 is a times -7 minus 2 plus 3 times -7 plus 7, which we know -7 plus 7 is 0, and 3 times 0 is 0, so that whole term is 0. -7 times 7, that's -49 plus 13, and then -7 minus 2, that's -9a, right? -49 plus 13, that's just -36. Right, so then if we divide by -9 on both sides, we'll just end up with a is 4. So now we have our capital A and our capital B, so we're able to rewrite our original integrand, right, the function we're trying to find the integral of, in this way. So this is where I was with my integral. I did all of my algebra to find capital A and capital B, and now I get to rewrite this. Right now I get to rewrite this as two separate fractions, and make sure that you keep, right, how you set up your a is over the x plus 7. You got to make sure you plug in a in there, and that you plug in capital B in here, right? Like you don't just flip-flop which one is capital A and which one is capital B. So capital A is 4, and that was over x plus 7, plus capital B, which was 3, which was over x minus 2. Okay, so now we have an integral where, right, like we can see this as two separate integrals over the addition sign. Remember, that was one of our properties. And next, remember, we can take out constant multiples. So I could simplify the fraction as 1 over x plus 7 dx plus, I pull out the 3, and I get 1 over x minus 2 dx. Remember, that's using that property of constant multiples. And then what do, right? Well, technically what we're doing is a u substitution, where u is x plus 7 and du is just dx, right? Because the derivative of x plus 7 is just 1, right? And then this one, we use a u substitution, where u is x minus 2. And again, derivative of x is just 1, derivative of -2 is 0, so that's just dx. So then this becomes 4 times 1 over u du plus 3, 1 over u du, right? And then we know the integral of 1 over u. We can do that with our antiderivative formulas. We know that that is equals to ln of the absolute value of u plus 3 times ln of the absolute value of this u, right? So maybe I should mark these as du1 and du2, just to be super specific. And then we have our plus c, since we have an indefinite integral. And then we can plug our u's back in. So we end up with 4 ln of x plus 7 plus 3 ln of x minus 2. And that is our final answer.